Welcome students to our last segment of factorial design, that is part 2. Remember from part 1 we introduced factorial design, we outlined when do we use factorial design, in other words the motivation for using factorial design, and we also went on to give some highlights of the historical perspective underlying factorial design. We finally concluded by looking at the types of effects in factorial design, where we looked at the simple effects, the main effects, and the interaction effect. And from the previous video, I gave you an example where you were supposed to understand or have an appreciation of what interaction effect is in factorial design. That is very, very important because this is the only design where we talk of interaction. So the previous video, please make sure if you did not watch that one, go to the last part where I requested you to produce profile graphs so that you have an appreciation of what do we mean when we say the interaction between factor A and factor B. Today, as we conclude, we shall look at factorial design and look at the various designs where factorial arrangements can be applied. Now, as introduction, we are saying the factorial design does not occur on its own. In fact, what we are meaning here, we are saying it is not just naturally that, okay, here we have factorial design. But what happens is that when we have two factors, the researcher must come up with the combinations, which we call the factorial combinations, and then test those combinations. And we are not supposed to just use the factorial design where we have a very large number of treatments, because the issue of homogeneity of the block will be affected. So if the treatment are so many, there is a tendency to have too large combinations, too large blocks, which makes factorial design a bit complex and less efficient. For most factorial experiments, the number of treatments is usually too large for efficient use of complete block design. That is exactly what I've already explained. Now, I have an example here. I want from the onset make it clear that all the designs that we have looked at so far, the complete randomized design, that is the CRD, the randomized complete block design, the Latin square, and of course you are going to look at the final design, which is the split plot. All those designs, we can have factorial arrangements. So we can have a randomized complete block design with factorial arrangement. We can have a complete randomized design with factorial arrangement, and we can have a Latin square with factorial arrangement. And I want you to appreciate when you look at the last segment that the last topic under experimental design, that is the split plot, that a split plot is actually a factorial design. So by factorial, we are simply saying we have more than two factors and above. We have more than one factor in an experiment. Remember from the last video, I gave a number of examples of factorial treatment combinations. Today, in this particular video, I've started by an example of a 3 by 5. We are simply saying 3 levels and 5 levels of a 2-factor experiment. So we have a 2-factor experiment with the 2 levels, with the 3 levels. One of the factors has 3 levels and the other one has got 5 levels. So we can actually have a 2 by 3 by 5, depending on the number of factors, where we have 3 factors. We can have the 4 factors, which in most cases, practically it becomes impossible. But that we can actually have a 4 by 3 by 2 by whatever. So here we've got 3 rice varieties. So variety is a factor. The different varieties, they are levels within the factor variety. And we've got 5 nitrogen levels. So these are the nitrogen levels. Firstly, there is no nitrogen application, that is 0. kilograms per hectare, 40 kilograms per hectare, 70 kilograms per hectare, 100 kilograms per hectare, in that order, and we have the varieties V1, V2 up to V3. So what we have here are the treatment combinations. These are the combinations that are formed in this factorial. That is the factorial treatment combinations. So you can see there are about 15 combinations. So in a single block of an RCBD, you will need about 15 plots. This is what it means. You need about 15 plots. Something like this. Something like that. Something like that. Sorry, yes, something like that. So that's 1, 2, 3, 4, 5. 1, 2, 3. So each of these, in other words, in this plot, maybe you will put no nitrogen, N0, and also with the variety 1. All the other combinations will be put here in a single block, of a randomized complete block design. But this is exactly the randomized complete block design that Ms. Charamba introduced to you. The only difference now is that instead of having one factor, we are now having two factors. So that we can form treatment combinations from those two factors and then use the combinations as treatments and apply them to a particular block of an RCBD. Now, from that experiment, this is the data that was obtained, and I want to make it clear that this is variety 1, this one is for variety 2, and the last one, which is this one, is for variety 3. That is why the different colors: variety 1, variety 2, and variety 3. Now, I want you to take note of the layout. So what we have just done here is to give nitrogen levels, 5 levels of nitrogen, this one, which belongs to variety 1, and we put the values across the different replicates. So they were replicated 4 times, so we expect N0 for V1. Remember the combinations: N0 V1 in replicate 1, in replicate 2, in replicate 3, in replicate 4. Why we are laying the data this way is to enable us to get the treatment totals, because we need, for each combination, for across the replicates, we need the total. And of course, we have the replication totals here below. Now, for purposes of fitting in a factorial ANOVA for RCBD, we lay our data in such a way that for each level we are able to get the total, and for each level of a variety we are able to get the total. So this is just what we are getting from here. So when you are given the data in this manner, you must make sure you rewrite the data in such a way that V1, V2, V3, 1, 2, 3, 4, 5, see, across the different replicates. So variety 1 in replication 1, what was the value in replication 2, in replication 3, 4, and 5, and you also do the same for, in other words, you can easily see here that we have got V1, V2, and V3, but we want the totals for V1 in replication 1, replication 2, in replication 3, in replication 4. Then we do the same for N1 in replication 1. N1, we just add this one, that is for replication 1, and we also add that one, and we also add that one. That is for N1, we have 3 values to be added. So when you do like that, this is what you are going to get. This will enable you to get the total for N1, for N0, N1, N2, N3, N4, for variety 1, variety 2, variety 3. Right. This is important. Check the layout. Nitrogen totals, variety totals. And take note that we are getting this from this table. Now, the statistical model, this model is for a single replicate. This is very, very important. For a single replicate. But when we have in our case, we have got more than one replicate. Remember, we have 4 replicates. So our model must also include the let me say, the other, we have to add the other component here, so that yijk is equal to mu plus tau I plus beta j plus rk. That is very, very important, plus rk, where we are talking of the kth replicate now. We need to add rk to our model. Take note of that for a randomized complete block design. Now, mu is the overall mean. Tau I is the effect of the ith level of factor A. So you can see our variety, we've got 3 varieties, so we'll have V1, V2. Our I will change from 1 up to 3 because we've got 3 varieties. Then for beta J is the effect of the jth level of factor B. Factor B is nitrogen. So we will have nitrogen N0, N1, N2 up to N4. So our B will be 4. So that our J changes from 1 up to, from 0 up to 4. J will be equal to 0 up to 4. I'm just relating to our example. This is a general statistical model for an RCBD experiment with factorial arrangement. So the most important component also that we have to talk about is the interaction component. So that is the interaction between the different levels of the factors. Interaction between the different levels of the factors, and of course the random error term that is associated with the kth replicate. Remember, we said the replicate is k, kth replicate in the ij cell. So for the ith level, jth level of factor A and B respectively. Now, we need to have an appreciation of this statistical model because it helps us to understand how the total sum of squares will be broken down in an analysis of variance. So you can easily tell from here that, okay, the yield, the ith variety, jth nitrogen level in the kth replicate yield is partly constant, but will depend on the variety, on the ith variety. It will also depend on the jth nitrogen level, and of course on the interaction between the variety and the nitrogen level, and also the replicate in question as well as the error. So we are going to have the SSR, SSA for variety, SS nitrogen, SS interaction, SS error. By looking at the statistical model, that is why we introduced this statistical model, because it helps you to appreciate how the total sum of squares will be broken down into the different components. Like what I said, this is going to be our analysis of variance. You can see that the analysis of variance has got the replication, the treatment. Of course, when we ask you to have an ANOVA, we normally ignore this part. So we will have, but I included this. I will explain to you why. This one, I included it to make it easy for you to calculate the interaction. So we have got the replication, variety A, variety, which is the factor A, nitrogen, which is factor B, and the interaction between variety and nitrogen, the error and the total. One person might ask, do I memorize these components? My answer is no. What you need to appreciate is that for the degrees of freedom, degrees of freedom, we are saying how many replications do we have? We've got R replications, so we subtract 1. So since we've got 4, we are saying 4 minus 1 to get 3. For the total, degrees of freedom for total, we ask ourselves, How many observations do we have? If you doubt it, my dear student, go back to the big table. Check the table from the accompanying notes. That table has got 60 observations. So how do you get 60 observations? You say the levels of factor A, 3 varieties, times B, which is 5 levels, 3 times 5, which is what? 15. Number of replications, 4. So 4, 3, 5. So you multiply, you get 60 minus 1, that will give us 59. Now, for nitrogen, number of levels of factor B minus 1, straightforward. For variety, A minus 1, it's 2, which is straightforward. Now comes the interaction. Interaction, we are saying A times B. The same way we are multiplying these factors, we also multiply the degrees of freedom to get the degrees of freedom for interaction. Now the big question is, what about for error? What about for error? For error, I want us to take note of the fact that this is important, my dear students. Take note of this one. We are saying SS total. I want you to use this. SS total, which is SST, is equal to, remember the breaking down of from the model, Yijk. SST is equal to, we will say, firstly, it will be SSR, that is the RK, SSR plus SSC A, the other factor, plus SSCB. Sorry, my pen is delaying, but this is important. I want you to get this. SSB plus the interaction, remember, SSAB, then finally plus the error. Remember the EIJK, which we have, so we say SS what? SS error. SS error. Dear students, this is important. We are getting this from where are we getting this? From the model. Let me just flip so that you see the model. This is the model, and I've added RK, remember, to the model. So when you come, you can see how the components, this is our SSE, SSAB, SSB, SSA, SSR. So you can see this is what we have. So with this, we use this to find the degrees of freedom for error. So you just say, once you can easily find the degrees of freedom for total, 59 minus 8 minus 4 minus 2 minus 3. That will give you 42. That is the degrees of freedom for error. So SST minus SSR minus SSA minus SSB minus SSAB will give us SSE, which are the degrees of freedom for error. Now, let's move on. The next question is, how then do we calculate the different sum of squares? Because we need these different sum of squares for a two-factor RCBD experiment. So we need the degrees of freedom. Very easy. First of all, we need to get the correction factor. How do we get the correction factor? Is the grand total over the total number of observation. So if you come to this table, our grand total is this one. We divide by the total number of observations. So we will have that divided by 60. That will give us this one as our correction factor. Now, how do you get the SST? SST, go to the original values. This squared plus this squared plus this squared plus this squared. You add the square of everything up to the last value. So you add the square of all the 60 values. I'm sure this is clear. So we are adding each 3.8, 5 squared plus up to the last value. Then we subtract the correction factor, and this is what we are going to get. Take note, dear students, that SST where I put just one summation, this is for simplicity. The correct notation would be sum. We need 3 summations actually. Sum of y. So we are summing over a, over b, and over r. Remember, we are summing over replications, over factor level b, over factor level a. But I felt this becomes cumbersome to put this here. So we just write one summation of y squared, and I removed the subscript. But all those things are supposed to be here. It must be sum over I, over j, over k. We are summing over all these variables. So you sum the original values. Now let's move on to what is SSA. Very easy. We are using this data. SSA. So we are squaring this squared plus this squared plus this squared. And we divide by what? It's important. So the total for A, all the totals for A squared divided by R times number of levels of the other factor. That is very, very important. This is very easy. SSA, you don't divide by the number of levels of A again. You divide by the number of levels of the other factor multiplied by the replications, of course. So that, but you have to subtract the correction factor, you get that one. SSB, using the same argument, totals of B, each sum of B squared, you divide by R times the number of levels of the other factor, not the one that you are finding. Very easy. Subtract the correction factor, that will give you that one. Now SSR, ladies and gentlemen, we are following the same pattern. We get the totals for R. Remember, the totals for R, they are on this table. On this table, this squared plus this squared plus this squared plus this squared. So you sum those ones. You are no longer dividing by the number of reps like what we have said. You divide by AB. You divide by AB minus the correction factor, so you get 2.599. Then SS treatment. Remember that table, the first table. Look at the first table, which is also showing on your notes. So we add the totals for the treatments. We divide by R, by the number of replications. This, let me just go to the data so that you understand. Remember, when we were calculating the sum of squares for under CRD or under RCBD, when we sum this, the square of this plus the square of that plus the square of this up to the end, we divide by the number of reps, not by the number of treatments. That is important. So we divide by 1, 2, 3, 4 to get S treatment. Now, we now have all the sum of squares which are needed for us to find the, to have an ANOVA table for a 2-factor RCBD experiment. So we put that one, replication, now have this, just replaced by the sum of squares, sum of squares, sum of squares, sum of squares. We put our degrees of freedom. Like I said from the beginning, this one normally we exclude it. We don't even need to add this one, so that we have replication, variety A, nitrogen B, A by B, error, and total. Those are the only components that we need for our ANOVA. But importantly to note is that SSAB, which is the interaction, is equal to SS treatment, SSA minus SSB. This is important. The interaction between two factors is equal to SS treatment minus SSA. There are so many ways of calculating. So once you are able to get the sum of squares due to treatment, you just subtract the sum of squares due to one of the factors minus sum of squares due to the other factor, you get the interaction of those factors. So this is the approach that I've used here. use any approach which is easier for you. And how do you get those approaches? Go through a number of textbooks, check how they get the interaction, and use the one which is easier for you. So I calculated SS treatment to help you to find the interaction. So, ladies and gentlemen, like what I said, you put your degrees of freedom. For interaction is just the degrees of freedom for A, degrees of freedom for B. You multiply the two, you get this one. That is the degrees of freedom for the interaction. So replication, you have this one. That is number of reps minus 1. Once you get these degrees of freedom, that is this one. You get this one. You get this one. You get this one. To get this one, you just subtract the degrees of freedom for total, which I shall call box, minus this, minus this, minus that, minus that. Now, this analysis of variance is key for testing 3 hypotheses. As you can see here, I have F for interaction, F for nitrogen, F for variety. So we want to see if the different varieties produces same yield on average. That is our null hypothesis, versus at least one variety differs from the rest of the varieties. So we use this. And take note that we compare this value here, this F cal, we compare it with F numerator 2, denominator 42. Numerator 2, denominator 42, at alpha, of course, 0.5. Please, ladies and gentlemen, I'm not going to show you this. Go to the statistical tables for a F. Fisher's tables, go to the statistical tables. Look out for this value. You go for the table, this is 0.05, please, pardon me here, this is 0.05, because we are doing it at 5%, but any other percentage, it's possible. You can do it at 1% or at 10%. I'm doing the test at 0.05. So you go under the F tables. So you will have your numerator, denominator, you know, the F table is arranged in this way. So there are denominator, numerator degrees of freedom, denominator degrees of freedom are listed here. Numerator are listed in a row like this. And then the alpha 0. The table, each alpha has got a separate table. So this is the 0.05. So you go under numerator, maybe you look for 2, then you come down to 42 for your denominator. So where the two intersect, here, you find a value. So the decision rule will be to reject H0 if your calculated value, which is this one that we have calculated on the ANOVA, is going to be greater than this one. So please do the test and make a conclusion whether the varieties, they have same yield on average or not. Then you do the same for nitrogen, except that the F critical will be F84 because the numerator is now 4, but denominator still remains 42. Then you test the significance of the interaction. It will be F at 8, for numerator 8, denominator 42 degrees of freedom at alpha. So those are the 3 hypotheses that we need to test. Interaction is significantly, interaction is the same across versus no, there is one interaction level which is different. And also nitrogen levels produces similar yield across versus there is at least one nitrogen level which is different from the rest. Varieties are the same, that is our H0. Varieties are the same. All the 3 varieties are the same on average in terms of yield. There is at least one variety that produces different yield from the rest. So those are the hypotheses to be tested by this. We don't just produce an ANOVA for the sake of it. We want to test a claim. We want to test a hypothesis. Now, I gave a CRD example, which I did not work out, but I gave you the solution. So nitrogen dioxide is an automobile emission pollutant, but less is known about. So you can read, just to go through this example. It's also on the attached notes. Then this is the data for CRD. Remember, for CRD now the model will change, will not include the RK. So the model will just be Yijk is equal to mu plus tau I plus beta j plus tau I plus tau beta ij plus eijk. So that is for CRD. The model will, you just remove the RK because we don't have blocking in a CRD. Remember, I think Ms. Charamba emphasized that we don't have blocking because we are doing the experiment either we are doing the experiment in a controlled environment, actually in a laboratory where we expect conditions to be almost uniform, so we don't expect any intruder. So this is an example of a CRD. I want you to work out and make sure you are able to appreciate how to get the different sum of squares. This is what you must get when you work properly. This is what you must get. Exposure, and you appreciate the degrees of freedom, my dear friends. Appreciate the degrees of freedom, how I'm getting them. The days, exposure by days, error, and total. Appreciate where these are coming from. Appreciate also where these are coming from. And I put a full stop, a question mark, a question mark. I want you to get the degrees, sum of squares for error and sum of squares, the total sum of squares. Play around with the layout of the data. Lay out the data properly following the example that I've already given, and make sure you are able to calculate this. These ones are straightforward. I know you are just dividing each sum of square by its degrees of freedom, and then these are the different F's for testing if exposure is different days, and also the interaction. But also make sure you complete all the missing things. Here I think we need the MSE, the mean sum square for error. We need, but for you to get that one, first of all get the sum of squares for error, SSE, here, and then you get this one. So you need to get two values, this one and that one. And then once you get this and this is what we use also to get this. So this is the question. Complete the remaining sum of squares, test all the. A good student would actually get the data. Don't look at the solution. Don't look at the ANOVA table. Get the data. Try to fit in a CRD ANOVA. That will be helpful for you. Now the last part. I want us to look at the profile graphs. These are the profile graphs, the profile graph or the interaction graph for this data. Now, I want you to take note. I produced two separate ones, but I want the last one. I will use the last one. Now, what is simply happening here is that, remember, we are looking at interaction. How does exposure interact with the days? Is there an interaction between exposure and days? By merely looking at this profile graph or interaction graph, without even going to the ANOVA table, one must appreciate that no, there is an interaction. What do we mean? Interaction, from the previous video, we defined it as the response of a level of factor A to a change in the level of factor B. In other words, factor A is fixed, and then we change the level of factor B, and then we ask ourselves, how is factor A responding to the change in the level of factor B? So, when there is no interaction, we expect lines to be parallel, A, B. What do we mean here? If you look at this level here, whatever happens to B does not have an influence on A. But look at the control. The control is at this level. The serum fluorescence is about 138 or so in day 10. But when we change to day 12, you can see there is a slight increase. But when day goes to 14, it drops to this level. So it simply means that the exposure is responding to what is the day in question. What is the day in question? Now this is the same. You see the lines are crossing each other because of the interaction effect. So by mere looking at the profile graph or the interaction graph, one must be in a position to say whether there is interaction or interaction is not significant. But of course, from the ANOVA table, one is able to tell that indeed there is interaction by a formal test of hypothesis for the effect of interaction. So that formal can also be visualized. Instead of using the formal test of hypothesis for the significance of the interaction of two factors, we can actually visualize the effect through a profile graph or an interaction graph. So if we find something like this, lines are crossing like this, and we say maybe this is factor A and this is factor B, we can say, okay, there is interaction. Here there is no interaction. Sometimes this is a really extreme high interaction. Here there is no interaction, but we can have something like this, which is also showing moderate interaction. So if we compare this and that one, it will be moderate interaction. Ladies and gentlemen, in conclusion, all the designs that we have, the RCBD, CRD, Latin square, you can have factorial arrangements. So that the design will be randomized complete block design with factorial arrangement. Complete randomized design with factorial arrangement. A Latin square with factorial arrangement. Disadvantage of which then will be you can't easily get interaction because of the complete additivity assumption for the Latin square. So as you go through this video, use the notes. Do as many examples as you can. That will make life very easy for you. Thank you very much. I hope justice has been done, and by now you are able to appreciate what factorial experiments are and how do you get the ANOVA for RCBD and ANOVA for CRD. Thank you very much. Enjoy your online.